Okay, new homework out yesterday, due a week from today. Second, take out a sheet of paper with the name, student ID, and pass it around. Take out a sheet of paper with the name, student ID, and pass it around. Take out a sheet of paper with the name, student ID, and pass it around. Just so we understand, Dr. Eschenberg does not punish people for not attending the class the day before Good Friday. That would be rude. But Dr. Eschenberg does reward the people who do show up the day before Good Friday. Thank you. So to the people who are watching this at home, sorry kids. Also, one of the fun things that I do is I'm going to take this enrollment sheet, compare it to those who chime in on Top Hat, and see who Top Hatted and who didn't sign the sheet, because I can guarantee one of you, it's fine. You can text your friends all day long, and if they enter in on Top Hat but they didn't sign the sheet, I'll know who they are. So, let's go. Light, when you ask yourself the question, is it a wave or is it a particle? I know. And do we think we're going to go the full time? No. Yeah. So if I could just have your attention for the next 45 minutes to an hour, we'll all get out of here. There we go. Huygens principle. Huygens principle talks about wavelets and wave fronts. If you had light, Huygen, say that this is a light wave. Really, Huygens principle says that if you want to figure out where this wave is going and how it behaves, you treat it as a series of wavelets. So what you do is on the line, you draw a series of dots, and then you draw circles around those dots. And what that does is it lets you know where that next wavelet or wave is going. So you would do the same thing, put your dots down, draw your circles, and it does get kind of messy, but you then wrap an envelope around it, or line, and so as you can see, line, dots, circles, draw new line. Line, dots, circles, draw new line, and this continues. And so this is this is how you would figure out what the waves are doing. Now, in a situation where you've got a wave passing through a slit, what you do is your wave front is right here, so you draw your dots and then you draw your circles, and what happens is the new wave front looks like a little bit of an arc. And then you draw dots. And then you draw your new circles. And then you draw your new wave front. So really, a lot of people think that with light, if you've got light coming in like this, the light that meets the slit will just continue on in a straight line. But rather, if it hits this, that light ray will actually scatter. It will fan out. Now, what we do is we add to this whole system, and we've studied it before, is constructive interference. That if you have waves that are coming at each other, bump to bump or trough to trough. Oh. That when they come together, they form a bigger wave and then continue on.
Is this only for light waves?
Light, it doesn't light, sound, all sorts of stuff. But for our purposes, it's going to be light. Trough to trough, it makes a deeper trough, and then the troughs move on. So this is an example of constructive interference, that the waves come together and make a bigger wave, either a bigger trough or a bigger hump. Then there is the idea of destructive interference, where if you have a peak meeting a trough, they come together and they form nothing. Now, for one brief instance, those waves do exist, but the observable part is not there. And then once you have time, go on a little bit, the waves separate and reappear. And so if you guys were I'm not doing it today, obviously, but if you guys wanted to study waves and what happens, you would need to understand the concept of, we live in a world of real numbers that you can wrap your mind around. But there are numbers such as imaginary numbers, complex numbers. The math gets deep, and the math helps explain how the waves can appear to be not there, but in reality they're still there, and they move on. Yeah.
So are you saying that if you have a peak and a peak coming towards each other, then they're going to create one peak. But if you have a peak and a trough, then they will
Cancel each other out.
Okay.
For one brief moment. The waves are still there, yes.
Okay.
And this is called destructive interference. The waves are interfering with each other, and the waves effectively disappear.
So it's as if you had positive one.
Yeah. Now, as an example, we have, let's say we have two sources of light, and the lines that I draw are the peaks, which means the valleys are at points halfway in between. And the source for this one I'm going to do in red. So where you see where the lines cross, that's a peak meeting a peak. And so points such as there, all over the place, that is a point of constructive interference. Now, where the gaps meet, that's like a trough meeting a trough. So there. That's also a source of, or a point of, constructive interference. A trough meeting a trough will give you constructive interference. In green is where a trough meets a peak. So it's on a line of one and in the gap of another. So that could be, you're on a peak of this wave, but you're between the red wave, so that's a peak meeting a trough. Peak meeting a trough, peak meeting a trough. They're all over the place. You got to be on one line, but in the gap of the other. So this is line, gap, but a line gap, that's where destructive. So in this situation, we're used to force, which is a Newton, and I didn't bring the book, but I'm just going to use what I'm used to. Force, when you play with it for a little more, you can get energy. And when you compare energy, you add in time, you can get power. So power is just the energy transferred per time. And we can call that a watt. But then if you take power and divide it by area, you get intensity. And the units that we're going to use for this are just watts per meter squared. So the light coming from the ceiling has a certain amount of power. So a certain amount of energy is coming down onto the floor. How would we be able to increase the intensity of the light coming down? Well, you can either A, increase the power coming out of the lights, or decrease the area that the lights are allowed to shine down upon. So if we took all these lights and aimed it effectively, arranged the lights so it could all focus on one point, it would be bright. And if we just got brighter lamps, it would get brighter anyway. We would increase the intensity of the light. Now, for this intensity, you can think of it as also as the magnitude of the waves. So this peak and peak will produce a big peak, and this is bright. A trough meeting a trough will give you a big trough, and again, we have bright. Because the energy is there, the energy is in the electric fields and the magnetic fields going in the opposite direction of what it is for peak to peak. But for peak meeting trough, you get dark. So in the areas of destructive interference, you would get a dark spot. You would get an area where of low intensity. So there are, when we do the thin film, or not thin films, we will do the, we did thin lenses this week. We're gonna do single double slit the following week, and then we do our show and tell the week after that. And then we're done with lab forever. Yes. Okay. Hold on, I can't hear you. This is the fan. I would say, only thing I would add is simple, non-destructive, non-harmful. It's been up there for 3 minutes. Pick up the pace. I mean, really, what do you do with it? So, are we done? May I continue? Oh, sure. Hold on. The class, I'm stopping the class and just going. We're all going to look at our what's the question. Okay. It's not fair. Honestly, there are good questions and bad questions. Yours, good questions. The circles coming out of the upper dot are all in black. Now, honestly, in the video, the colors are, yeah, they're coming much better in the video. It's this Elmo that is dumb. The lines coming out of the bottom one are red. Well, where the lines meet the lines, I think those are black. Where the gap meets gap, that's red. Where a line meets a gap, that's green. Yeah, and you can even tell the upper one, that looks bluish, the middle one is red. Or you just discovered it. Yeah, I get it. I understand. Look, we're gonna get extra points out of this. Just lighten up a bit. Yeah, to those of you who are late, I forgive you. Make sure A, you do the top hat, and B, there are 3 sheets of paper going around. Make sure your name and student ID is on it. In next week's lab, you will have situations of single slit, double slit, and diffraction grating. Now, diffraction grating, you're not really gonna, there may be a demo on a table up front, but in terms of the lab itself, the big guys are the single and the double slit. In all three cases, you have a screen, which is there. You have a light source, which will be, if you've never played with a laser before, now's your time. It's gonna be next week. Huh? How big? It could burn your eye out if you let it, if you aim it at somebody for long enough. I'm not. So in the single slit and the double slit, single slit, what happens is they give you a slide, and in the slide where there should be a picture, it's a piece of aluminum foil, and in the aluminum foil there's a cut, a series of cuts. In the double slit, you got another slide, and it's a series of double cuts. So when you look, you can look at it, it's really tiny, but it's a series of two slits right next to each other. And in the diffraction grating, they give you this slide, and it looks, you look at it and go, where are the lines? It's because it's a series of, it looks, if you look at it with a microscope, it looks like a series of fibers, line to line, right next to each other. So, I mean, a very bad example would be, if you looked at it really close, it would just be like these pins, equally spaced, but instead of being pins, they would be strings. In all three cases, you have the distance L. The distance L is obviously the distance from the screen to the slit. So you're going to need to know that. Approximately a meter, because that's what you deal with on your workbench. In a single slit, we use capital D, and it's the width of the slit. In a double slit, we use D, and D is the distance between slits. In a double slit, you don't care how wide the slits are. You're more interested about the width between, or the distance between the two slits. In the diffraction grating, you also use little d, and little d is the distance between the strands, not strange, strands of the grating. I can't spell, I don't care. In all of these situations, constructive and destructive interference occurs. Now there is a theoretical explanation as to why these equations do what they do. I'm not going to go into the details about it, but what I will say is that the single slit is interested about minima only. It only cares about where the dark spots are. That's what the equation does. And the equation that you use is d sine theta equals m, or lambda L, or lambda m, m lambda, either one. D is the width of the slit. Theta is the angle down or up from the central axis, or the optical axis. So theta is the angle up or down from the optical axis. Yes. Is it what? No. Excellent question. It's the angle from the center down to whichever dark spot you're looking at. Once again, there are dumb questions, derpy questions, good questions, and great questions. Very great questions, because it's honestly, it's a clarification. Excellent. It's an angle up or down from the central axis to whichever minima we're talking about. In a diffraction grating, diffraction gratings only care about maxima. The maxima, or bright spots, once again, you use the same things, where instead of big D sine theta is m lambda, it is little d sine theta m lambda. And that deals with maxima only. And once again, theta is the angle up or down from the optical axis to whichever maxima you're talking. What is what? Now, M, we're getting to this. Not done with the lecture. Because what I'm doing is I'm giving you the equations, and I'm going to draw a lot of pictures, and then the M's will become evident. Would you like for me to pick that up for you? Okay. In the single slit, it is minima only we care about, the dark spots. Diffraction grating, maxima only. The double slit, we can study minima and maxima. Now, for the minima, or destructive, it is d sine theta m plus 1/2 lambda. Now, obviously, lambda, just so for people at home, lambda is the wavelength of the light that you're pumping through this. For maxima, or constructive, it's d sine theta m lambda. These are the equations that you use. If I say you've got a single slit, boom, write that down. You've got a diffraction grating, boom, write that down. If I say you've got a double slit, your question is it destructive or constructive? Because I got to use the proper equation. When you look at single slit, double slit, diffraction grating, what I'm going to do is draw the intensity. So on all of these lines, if it intersects with this line, it's a dark spot. If it intersects, well, the higher it goes, the brighter it is. And what's really a shame, people talk about, yeah, like using demos. The demo that we have for this, it's like you end up seeing something that's like this big, and people in the back of the room, and even people like in the third row can't even see it. It's only the front row, the front two. In this vertical line right here, that's the optical axis. Think of this region up here as this region up here. Think that region down there is this region over here. So I effectively taken this and twisted it 90 degrees. For a single slit, it looks a lot like this. You have a very broad, bright band, or very broad, bright central max. And then you've got darks on either side, then bright, then dark, then bright, then dark. And the bright spots get dimmer the further away you go. Because in reality, the light is kind of like if you're firing a shotgun at a little hole in the wall. The shotgun pellets, a lot of them make through and then they start scattering, but they kind of maintain their momentum. And so this is the central blast zone, and then there's a few pellets that kind of scatter off, which are these. For a double slit, it looks like this. I'm drawing it horrible. So what you do is you've got a narrow, bright, central max. And then you've got this whole never-ending, this rapidly oscillating, gentle oscillations, and these are rapid oscillations. It's very jagged. When you next week, when you look at the lab and you turn on the single slit, you're gonna go, oh, that's very nice. It just kind of broadly goes out and blah blah blah. But when you use the double slit, it's like, oh my goodness, it's just a whole bunch of little lines. For the diffraction grating, it looks like this. So with the diffraction grating, it is a narrow, bright, central max, and then you've got a whole bunch of little oscillations, but with spikes on either side at particular distance. So with this, the light gets bright and then it fades to dark and then it gets bright and then it fades to dark, etc. For diffraction gratings, it's bam, I'm here, nothing. Bam, nothing. Bam again. So it's these massive spikes amidst nothing. Now, someone asked the question, well, what's M? M denotes, M is the, some call it the order. It's the label of the max and min. When you're dealing with single slit, the minima are there. This is the central max, but you don't really care about it. All you care about are these. M equals 1, M equals 1, M equals 2, M equals 3, M equals 2, M equals 3, etc. So for a single slit, the M's that you use, M is equal to 1, 2, 3. 0 is not used. 0 would produce the angle at which the central maxima is located. The central maxima we're not concerned about for a single slit, so we don't use it. For diffraction gratings, or I'm sorry, for double slits, the minima are there, and they go 0, 1, 2, 3, on and on. For this is 0, 1, 2, 3, 4, etc. So the minimum, yes?
So do we not use negative and positive to denote which direction those are going?
No, in the problems that I assign, I generally say above or below.
Okay.
In this particular case, no, I wouldn't, don't use negative symbols.
Negative is
Just
not
no,
allowed. Okay.
yeah. So for the destructive, M is equal to 0, 1, 2, etc. Single slit, you don't use 0 for minima. Double slit, you do. The way that they get around it is they add a 1/2 in the derivation. The maxima, 0, 1, 1, 2, 2, etc. The maxima, M is 0, 1, 2, etc. The one thing to note is there is only one max where M is equal to 0. But there are 2 mins where M is equal to 0. There are 2 zeros, minima, over there and over there, but only one central max, so there's only one where the maxima is 0. In these spikes, M is equal to 0, 1, 2, 0, 1, 1, 2, 2, etc. So if I said you've got a central max where M is equal to 1, you know I'm either talking about this one or that one. If I go, you got a min on a double slit where M is equal to 3, I'm talking about that or that. So what, yes?
So in the single slit, the M is denoted as minimum, but in the diffraction grating, the M is denoted as
Maximum. And in double slit, M can denote maxima or minima.
So how do you?
I have to tell you. In single slit, minima only. That's all we're dealing with. Diffraction grating, maxima only. Double slit, I'm gonna have to be specific. I'm gonna have to give you the information. Are we dealing with a bright spot, maxima, dark spot, minima? In all of these situations, you have the slide, you've got, are we comfortable? We are comfortable. Have your legs up and everything? We need recliners in this room, definitely. Okay, good, good. I'm all about the student, so your comfort makes me happy. So we've got the distance from the slits or the grating to the wall. We've got the angle theta. So if I gave you a series of information, you could find the angle at which that maxima is above or below. But in the lab, you are going to have, you're going to sit and measure distances. And the distance above or below the central maxima on the screen is little l. So if I go 3 centimeters above the central max, you get your little ruler out and then you measure 3 centimeters above. In single slit, let's say lambda was 800 nanometers and L was 1.2 meters. How far above the central max and let's say, oh, in single slit, I'm gonna have to give you, single slit is 0.5 times 10 to the negative 3 meters, or half a millimeter. How far above the central max on the screen is the M equals 1, actually, M equals 1 band. So you have the screen here. When you look at the pattern, those are the minima that concern us. This is the film. The single slit has a distance D. I want to know this distance L that's theta, that's L. I want to know the distance from the central max to the first minimum. In the equation, we use d sine theta is equal to m lambda. There's a problem with the equation. Sine theta deals with opposite little l that we don't know, that we're looking for, and divides it by the hypotenuse, which we definitely don't have. So we're kind of in trouble. So what they do is they use something called small angle approximation. Not approximation, approximation. When you've got, say you've got a 30-degree angle, tangent of 30 degrees is way different than sine of 30 degrees. But what you do is you can sit there and plug numbers in your computer or in your calculator. If it's 10 degrees, there's a little bit of a difference. If you're talking about 2 degrees, sine of 2 degrees and tangent of 2 degrees are about the same. The smaller the angle, the more sine theta equals tan theta when theta is small. So when sine of theta and tangent of theta are about equal to, when theta is really small, those two quantities are equal to each other, effectively. So if sine theta is equal to tan theta, this distance here is on the order of like a centimeter, 2 centimeters. This thing is on the order of like 1.2 meters. So if I do inverse tan of 0.02 divided by 1.2, I'm dealing with a number less than a degree. So these numbers you can approximate. And tangent of theta is L over big L. So this becomes dl over big L m lambda for a single slit. This be solved for little l. Now the numbers I just pulled out of thin air. 1.2, 1, 800 times 10 to the negative 9 over 0.5 times 10 to the negative 3. Hopefully we will get a coherent number. Otherwise, numbers I've never been fond of. So I get 1.9 millimeters. So that's okay. Yes?
Why can't, like, using the sine theta equation, why couldn't you just solve for theta and then use...
You could.
Good?
Yeah. But the thing... Trying to think of a coherent way to... oh yeah, I guess you could. I say that sine theta is equal to tan theta, which is equal to little l over big L. And I substitute that in for there. So d sine theta m lambda becomes d tan theta equals m lambda, which then becomes that. The thing, could you do it that way? Yes. The other thing is you need to know that and it is a worthwhile question. I'm not going to slam it, unlike some people that have asked other questions earlier. Well, not today. It's been a very good class. It's for situations where I ask for big L or little l, or there's certain things where, from a problem-solving standpoint, I'd rather have the student make one calculation, do one rounding, and that's it. The way that you're talking about is you solve for theta, and I know for a fact that you guys are going to round, which means you're introducing, in computer terms, you're introducing bit rot. You're introducing uncertainty, which will now fan out. And that's not something that I think is worthwhile. If I just said, give me the angle, like there are problems in that problem set on Blackboard now that say, there's one that says, give me the angle spanned from the second minima above for a single slit to the third minima below. So what you would do is you would get that angle and that angle and add them together. And then that's it. The small angle approximation works for single, double, and diffraction grating. Little L over big L is the substitution that you use for everything. We'll do one example and then we'll call it a day. You have, this is the one which it drives students insane. Lambda equals 800 nanometers. The distance between the screen and the slide, 1.2 meters. Oh, and there's another. We'll talk about. There's an evil problem that I do. Not this one. This one's evil. The next one is just on a whole new level. Give me the total number of bright and dark bands within 4 centimeters of the optical axis. So what's going to happen is you got this. I'm going to have a certain distance, 4 centimeters that way, 4 centimeters that way, and then I want you to count the bands that occur in between. Add them up. I don't want to know the number of bright and the number of dark. I want the total. Yes? Yeah, we're doing double. Yeah, and this, when you're counting slits, when you're counting brights and darks, this is a double slit. Little d, the distance between the two is 0.05 millimeters. So this is 5 times 10 to the negative 2 millimeters, or 5 times 10 to the negative 5 meters. The first thing that you want to do is make sure your slit distance and your lambdas are all in meters. So get that straightened out. Now what I'm going to do is I'm going to solve for M for both bright and dark. For bright, it's d sine theta equals m lambda. I'm going to use small angle approximation to do d sine theta becomes tan theta, which becomes L over big L, which is m lambda. So this is dl over L lambda is equal to m. For the dark, d sine theta m plus 1/2 lambda. And what we'll do is we could show the similarities between these two equations. D tan theta m plus 1/2 lambda, d little l over big L is m lambda plus lambda over 2. I'm distributing the lambda. Bring that over. dl over big L minus lambda over 2 is equal to m lambda. Divide both sides by lambda, and I get dl over lambda L minus 1/2 is equal to m. So really all I have to do is get this, deduct 1/2, and then I get the m for the other one. So this is m bright, this is m dark. Plug in the values. 5 times 10 to the negative 5. L, I'm looking for 4 centimeters of axis, 0.04. To find the m, all you need is the distance from the axis to the extreme. Do not use 0.08. What we're going to do is, we're going to get to that. Big L, 1.2. Lambda, 8 times 10 to the negative 7. And that gives me an m that hopefully works. And I get 2.08 minus 0.5, m dark is 1.6 effectively. So I'm going to use, I could use 2.1 and 1.6. Those are my m's. Now I've got a little bit of an extra, I've got extra numbers. I don't have whole numbers of m. I have to convert these to m. For m, always round down. What is happening here is I'm counting the maxima as the definition of what a peak is. So when you go 4 centimeters to the right, that distance is just beyond, just on the other side of the m equals 2 maxima. For little m, or m sub dark, it's beyond, the first m equals 1 dark band, but it's not, it doesn't reach the m equals 2 minima. You can't round up m's for a double slit. Only round down. Only round down. Only round down. I've said it 3 times. It's only for the, well, for the single slit, Actually, for all the M's, you always round down. And due to lack of time, we'll discuss more of that on Thursday or on Tuesday. And again, obviously, Good Friday tomorrow, no school, no tutorial. Go home, play in the yard, do something. So the total number are, I've got 0, 1 band, 2 bands, 3 bands, 4 bands, 5 bands, 5 bright. I've got 1, 2, 3, 4 dark bands. So the total is 9. You cannot have a fraction of a band. You either have a band or you don't have a band. You're either Van Halen or you're Nickelback. Not in between. I just made that up. I'm funny. All right. That's all we're going to do today. It's the same thing for the other types of slits and gratings. Have a happy Easter.